Hello, in this lecture I will answer two questions. In the first question, we find out the area of this green shape, and in the second question, we find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have a circle inside this big semicircle. We know that this is line segment AQ, that is equals to 4 units in its length. This is line segment TB, that is equals to 1 unit in its length. This is angle STB, that is a right angle. This is angle PQA, that is also a right angle. Again, our task is to find out the area of this green shape. So first of all, we define the radius of this big semicircle as x and the radius of this small circle as y. And we'll also define the center of this small circle. This point is point O. And we define the center of this big semicircle. This point is point C. We'll also define the point of tendency of tangent AB with this small circle. This point is point N. And we'll define the point of tendency of tangent ST with this small circle. This point is point L. And we'll define the point of tendency of tangent PQ with this small circle. This point is point H. And finally, we'll define the touching point of the small circle with this big semicircle. This point is point K. In the next step, we'll join points O and N together by a straight line. Point O is the center of this small circle. Point N is the point of the small circle itself. Therefore, ON is the radius of this small circle. That is equals to y according to our definition. The radius ON is equals to y. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO according to rule 1. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, that is a right angle. AB is the diameter of this semicircle. So AB is a diameter, it is absolutely a straight line. So if you focus on the upper side of this straight line AB, it's point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB, it's point Q. We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, this is angle STB, that is a right angle. So if you focus on the upper side of the straight line AB, it's point T. Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB, it's point T. We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and H together by a straight line. OH is of course the radius of this small circle, that is equals to y. The radius OH that is equals to y. The radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So inside quadrangle HO and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrangle HO and Q we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if not a square. So relate to this quadrangle HO and Q is a rectangle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle HO and Q, side HO must be equal to the opposite side QN. But HO is y, therefore the opposite side QN must be also equal to y units in its length. In the next step, we join points O and N together by straight line. OL is of course the radius of this small circle that is equals to y. The radius OL that is equals to y, the radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So inside quadrangle OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrangle OLTN, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle in front of the square. So in that quadrangle OLTN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. This is line segment QT. Line segment QT is part of the straight line AB. So part of a straight line must be also a straight line. Therefore QT is a straight line, and QT in total must be equal to QN plus NT. That is why QT equals to QN, that is y, plus NT, that is also y. So QT in total equals to 2y. AB is the diameter of this semicircle. The radius of this semicircle equals to x, therefore the diameter must be equal to 2x. So the diameter AB of the semicircle equals to 2x from one side, but from the other side the diameter AB of the semicircle also equals to AQ plus QT plus TB. Again, the diameter AB in total equals to AQ plus QT plus TB. So I write it down. AB equals to AQ plus QT plus TB. So 2x equals to AQ, AQ is 4, plus QT, QT is 2y, plus TB, TB equals to 1 unit in itself, according to what is given as the question. So in total, we actually found out that 2x equals to 4 plus 2y plus 1. So 2x equals to 2y, and 4 plus 1 is 5. So 2x in total equals to 2y plus 5. Here we subtract 2y from this equation, and we get that 2x minus 2y equals to 5. Here we take out 2 as a common factor from those two expressions. So inside the brackets we have x minus y. So today we found out that 2 times x minus y equals to 5. Here we will divide this equation by 2 and finally get that x minus y equals to 5 over 2. 5 over 2 is 2.5. In conclusion, we found out that x minus y equals to 2.5. What is the length of this 9/7 cn? From the drawing it is very easy to see that cn in total equals to cb minus nt minus tb. Again, cn in total equals to cb minus nt minus tb. So write it down. Cn equals to cb minus nt minus tb. This again, if we found out that Cn equals to Cb minus Nt minus 3b. So Cn in total equals to Cb. Cb is the radius of this semicircle. That equals to x. Minus Nt. Nt is y. Minus Tb. Tb equals to 1 unit in itself according to what is given in the question. So in total we should find out that Cn equals to x minus y minus 1. X minus y is 2.5, so we substitute x minus y here by 2.5. So Cn in total equals to x minus y 2.5 minus 1. 2.5 minus 1 is 1.5. So in total we found out that Cn equals to 1.5 units in its length. This is 9/7 cn, is equals to 1.5 units in its length. In the next step, I'll present to you rule 9. The rule that we have already talked about it in the previous lectures, and we will implement rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then if two circles touch each other internally, then the straight line that connects their centers together passes through their touching points. In the drawing we have two circles. The center of this big circle is 0 at point O. The center of this small circle is 0 at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through the attaching point, that is actually point P. If it again, the straight line OM must pass through point P, that is the attaching point. Or O and P is one straight line. Again, according to this rule 9, O and P is one straight line. So we can actually implement rule 9 in our drawing. In our drawing, we have an internal notch between the small circle and the big semicircle, that is to say, they touch each other internally, and this point K. And whenever you have an internal notch between two circles or semicircles, you can implement rule 9. So we implement rule 9 in our drawing. The center of this big semicircle is here at point C. The center of this small circle is here at point O. The straight line that connects the centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through the attaching point, that is actually point K. Again, according to rule 9, the straight line CO must pass through point K, that is the attaching point. Or COK is one straight line. Again, COK is one straight line according to rule 9. So we join point C and O together by straight line, and according to rule 9, the straight line CO must pass through point K, that is the attaching point. You can see in the drawing that indeed the straight line CO passes through point K, that is the attaching point. Or COK is one straight line. So it is exactly according to rule 9. The straight line CO passes through point P, through point K, that is the attaching point. So COK is one straight line, and therefore CO must be equal to CK minus OK. Again, CO must be equal to CK minus OK. So write it down. CO equals to CK minus OK. So CO equals to CK. CK is the radius of this semicircle, that equals to X. Minus OK. OK is the radius of this one circle, that equals to Y. So in total we should find out that CO equals to X minus Y. So the length of this line segment CO is equal to X minus Y. But we already found out that X minus Y equals to 2.5. Therefore CO that equals to X minus Y, it is equals to 2.5 units in its line. We already found out that Cn equals to 1.5 units in itself, and On is the radius of this small circle, that equals to Y. So in the next step, I copied the right triangle OCN in a new page, and we will implement the Pythagoras theorem on this right triangle OCN. According to the Pythagoras theorem, in any right triangle, the square of the apotropos equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle OCN. That I call it from the original drawing. This right triangle OCN, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. So I write it down. According to the Pythagoras theorem, in this right triangle OCN, OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. The hypotenuse OC equals to 2.5 units in its length, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared, plus Cn squared. Cn is 1.5 units in its length, Cn equals to 1.5 units in its length, therefore Cn squared is 1.5 squared, that is 2.25. So in total, we actually found out that 6.25 equals to y squared plus 2.25. Here we subtract 2.25 from this equation, and we get that 6.25 times 2.25 is 4, so 4 equals to y squared. Here we take a root out of this equation, and finally get that y equals to the square root of 4, that is 2. So the radius of the small circle y equals to 2 units in its length. We already found out that x minus y equals to 2.5. But y is 2. Therefore x minus y is x minus 2 equals to 2.5. Here we add 2 to this equation, and we get that x equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So in total we found out that the radius x of the big semicircle equals to either 9 over 2 units in its length, or in terms of numbers, the radius x equals to 4.5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the big semicircle minus the area of the small circle. The area of the green shape equals to the area of the big semicircle minus the area of the small circle. The radius of the semicircle equals to x units in its length, therefore the area of the semicircle must be equal to pi x squared over 2. Minus the area of the circle, minus the area of the small circle. The radius of the small circle equals to y, therefore the area of the small circle must be equal to pi y squared, which is minus pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total, the area of the semicircle must be equal to pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4. So pi y squared is 4 pi. We'll open the brackets in this of this expression, and you get that the area of the green shape equals to pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4, minus 4 pi. So this expression, the numerator of this expression, in the numerator we have 81 pi over 2 times 4 is 8. Minus 4 pi. So here we will multiply minus 4 pi by 8 and then we divide it by 8 in order to overcome factor of this expression. And we get that minus 4 pi times 8 is minus 32 pi divided by 8. 81 pi minus 42 pi is 49 pi. 49 pi over 8. 49 pi over 8 is 19.34 square units. And that is the answer to the question. Repeat again, if you found out that the area of this green shape, that is the area that you are looking for in this question, is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape is equal to 19.24 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our task was to find out the length of this line segment PQ is equals to x. We have to find out the value of x. In the domain, we have a semicircle. This is point O. According to what is given in the question, point O is the center of this semicircle. We also know that PT equals to TS. So if we define the length of PT as A, then the length of TS must be also equal to A because they are equal to each other. We know also that this is angle PTS, that is a right angle. This is angle PQB, that is also a right angle. This is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. Again, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the first step, we will complete the semicircle to a circle. We completed the semicircle to a circle, and we'll extend line segment TS by a straight line until it touches the circle. We define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we will join points P and M together by a straight line. By joining points P and them together with Sudan, you can do triangle PTM. Triangle PTM equals to 90 degrees in its size according to what is given in the question, and it's subset on chord PM. Again, triangle PTM, that is the right angle, subset on chord PM. So here we can implement rule 5. A bit quicker, rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subset on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN, that is the right angle, it is equal to 90 degrees in size. And according to this rule 5, peripheral angle MAN, because of the fact that peripheral angle MAN equals to 90 degrees in size, it must subset on the diameter of the circle. And indeed, peripheral angle MAN subset on MN, that is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in size must subset on the diameter of the circle. So can I implement rule 5 in our drawing? One put in our drawing. This is peripheral angle PTM, that is equal to 90 degrees in size. According to rule 5, peripheral angle PTM must subset on the diameter of the circle. Peripheral angle PTM subset on PM, and therefore PM must be the diameter of the circle. So write it down. If you found out that chord PM must be the diameter of the circle according to rule 5. According to what is given in the question, point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle. OB equals to OS plus SB. OS is 2, SB is 1, so OB in total equals to 2 plus 1, that is 3. So if you found out that the radius of this circle equals to 3 units in its length. OP is the radius of this circle, that equals to 3 units. OM is of course also the radius of this circle, is equals to 3 units in its length. In the next step, we will do a construction. That is to say, from this point S, we will draw perpendicular on the diameter PM. Again, from point S, we will draw perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. By doing this construction, we're going to do the right triangle ONS. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. So in this right triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha. This angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha. according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. Those two triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So we shall prove that all the angles of this upper right triangle PQO are correspondingly equal to all the angles of this right lower triangle OSN. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We have to prove that the upper right triangle PQO is similar. This is the sign of similar to the right lower triangle OSN, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle OSN over side PQ of the upper right triangle PQO equals to side OS of the right lower triangle OSN over side PO of the upper right triangle PQO. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the right lower triangle OSN over side PO of the upper right triangle PQO. SN is the missing side, so we leave it as it is, over PQ. PQ is the line segment that we are looking for in this question, and it is equals to X. We have to find out the value of X. And it is equals to OS. OS equals to 2 units in its length, according to what is given as the question. Over PO. PO is the radius of this circle. This equals to 3 units in its length. So in total, we should find out that Sn over x equals to 2/3. Here we will multiply this equation by x. And we get that Sn, the missing side Sn, is equal to 2/3 x. In the next step, we define this angle as beta. The size of this angle is equal to beta. And we will focus on the right small green triangle, triangle S and M. In the right green triangle S and M, this angle equals to 90 degrees. This angle equals to beta, and therefore this third missing angle must be equal to 90 degrees minus beta. Y equals 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PTM, this angle equals to beta. Therefore, angle beta is a common angle that belongs to both triangles. Angle beta belongs to the green triangle NSM. Angle beta also belongs to the big right triangle PTM. So in the right triangle PTM, this is angle beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. The right triangle PTM is similar to this green small triangle NSM, according to angle similarity rule. That is to say, first of all, this is angle beta, that is a common angle that belongs to both triangles. So we can write down that angle beta equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if we prove that all the three angles of this big right triangle PTM are correspondingly equal to all those three angles of this right triangle NSM. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle PTM is similar to this small green right triangle NSM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SN of the big side SN of the green triangle SNM or side PT of the big right triangle PTM equals to side SM of the green right triangle SNM or side PM of the big right triangle PTM. Okay, again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side SN of the green right triangle NSM or side PT of the big right triangle PTM equals to side SM of the green right triangle MSN or side PM of the big right triangle PTM. We have already found out that SN equals to 2/3 x over PT. PT equals to A units in its length, according to our definition. And it is equals to SM. SM is the missing side, so we leave it as it is. Over PM. PM is the diameter of this circle. The radius is x, therefore the diameter must be equal to 2x. The radius is 3. The radius of this semicircle equals to 3, therefore the diameter must be equal to 6. 3 plus 3. So the diameter PM equals to 6 units in its length. So in total we should find out that 2/3 x over A equals to SM over 6. Here we cross multiply this equation. And we get that 2/3 x times 6 equals to ASM. After we cross multiply this equation, I should find out that 2/3 x times 6 equals to ASM. 6/3 is 2, and 2 times 2x is 4x. So in total, in this side of this equation, equation 1, we have 4x. 4x equals to ASM. According to equation 1, 4x equals to ASM. And again, according to equation 1, we found out that 4x equals to ASM. In the next step, I'll present to you a rule that we already talked about it in the previous lectures, and we'll implement the rule in our drawing. The rule is rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the drawing we have a circle. This is called AB that intersects with chord CD at point O. So in this drawing the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Why? Because in our drawing we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement in our drawing rule 15. So I write it down. We should find out that in our drawing chord TM intersects with chord AB at point S. The intersection point occurs at point S, this point. So according to rule 15, the following equation will be true, that TS times SM equals to AS times SB. Repeat again, according to rule 15, the following equation will be true, that TS times SM equals to AS times SB. This will be equation 2. TS equals to A units in its length according to our definition, times SM. SM is the missing side, so we leave it as it is. And it is equal to AS. AS in total equals to AO plus OS. So AS in total equals to AO, that is the radius of this circle, that is equals to 3 units in itself, plus OS. OS is 2. So in total, AS equals to 3 plus 2, that is 5. Again, AS equals to 5 units in its length, times SB. SB equals to 1 unit in its length, according to what is given as the question. So in total, according to equation 2, if we found out that A times SM equals to 5 times 1. 5 times 1 is 5. So in total, according to equation 2, if we found out that A times SM equals to 5. This is according to equation 2. When according to equation 1, we have already found out that A times SM equals to 4x. According to equation 1, we have already found out that A times SM equals to 4x. So we have two different equations for the expression ASM, A times SM. Therefore, we create the equation 3 that states that A times SM according to equation 1 must be equal to A times SM according to equation 2. Repeat again. Equation 3 states that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times SM according to equation A times SM according to equation 1 equals to 4x, and it must be equal to A times SM according to equation 2. A times SM according to equation 2 equals to 5. So in total, if you found out that 4x equals to 5, according to equation 3, if you found out that 4x equals to 5. Here we will divide this equation 3 by 4, and finally get that, according to equation 3, x equals to 5 quarters. 5 quarters is 1.25. So if you found out that PQ is equals to x is equal to either 5 quarters units in itself, or in terms of numbers, PQ is equals to x is equal to 1.25 units in itself. PQ is equals to x is equals to either 5 quarters units in itself, or in terms of numbers, is equals to 1.25 units in itself. So finish with the second question. So in the next step, I'll summarize the lecture. I'll start with the first question, of course. Our task in the first question is to find out the area of this green shape. So in the drawing we have a circle inside this big semicircle. We also know that this is line segment AQ, that is equals to 4 units in itself. This is line segment TB, that is equals to 1 unit in itself. This is angle STB, that is a right angle. This is angle PQA, that is also a right angle. Again, our task is to find out the area of this green shape. So first of all, we defined the radius of this big semicircle as x and the radius of this small circle as y. In addition, we define the center of this small circle, this point is point O. We define the center of this big semicircle, this point is point C. In addition, we define the point of tendency of tangent AB with this small circle, this point is point N. Likewise, we define the point of tendency of tangent ST with this small circle, this point is point L. We also define the point of tendency of tangent PQ with this small circle, this point is point H. And finally, we define the touching point of this small circle with this big semicircle, this point is point K. In the next step, we join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of this small circle, that is equals to y according to our definition. The radius of N that is equal to y, the radius of N is known to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, that is the right angle according to what is given as the question. AB is the diameter of this semicircle. AB is a diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to the same rule 3. So which angles we have at the upper side of the straight line AB at point T? We have this angle that is a right angle according to what is given as the equation, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join point O and N together with a straight line. OL is of course the radius of this small circle, that is equals to y. The radius OL that is equals to y. The radius OL that is equals to y. The radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So in quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OLTN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of square. So we write to quadrilateral OLTN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OLTN, side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. In the next step, we join points O and H together by a straight line. OH is of course the radius of this small circle, that is equal to y. The radius OH that is equal to y, the radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in quadrilateral OH and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HO and Q, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of the square. So in order to quadrilateral HO and Q is a rectangle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So rectangle HO and Q, side HO must be equal to the opposite side and Q. But HO is y, therefore the opposite side and Q must be also equal to y units in its length. Line 7 QT is a straight line because it is part of the big straight line AB. So QT is a straight line, and therefore QT in total must be equal to QN plus NT. That is to say, QT must be equal to QN, that is y, plus NT, that is also y. So QT in total must be equal to y. AB is the diameter of the semicircle, therefore it's twice as long. It is twice as long as the radius. The radius is x, therefore the diameter AB must be equal to 2x. So the diameter AB of the semicircle, from one side it is equal to 2x, But from the other side, AB also equals to AQ plus QT plus TB. Again, AB in total equals to AQ plus QT plus TB. So from the other side, AB in total equals to AQ plus QT plus TB. AQ is 4, QT is 2y, and TB is 1. Again, AQ is 4, QT is 2y, and TB is 1. So in total, 2x equals to 4 plus 1 is 5, plus 2y, or 2x equals to 2y plus 5. Here we subtract 2y from this equation, and finally found out that 2x minus 2y equals to 5. Here we took 2 as a common factor from those two expressions, so inside the brackets we left with x minus y. So 2 times x minus y equals to 5. Here we divided this equation by 2, and finally found out that x minus y equals to 5 over 2, or 5 halves. 5 over 2 is 2.5, so x minus y equals to 2.5. What is the length of this line segment Cn? Cn equals to Cb minus Nt minus Cb. Again, Cn in total equals to Cb minus Nt minus Cb. Okay, again, Cn in total equals to Cb minus Nt minus Cb. So Cn in total equals to Cb. Cb is the radius of the semicircle, that equals to x. Minus Nt equals to y, and Tb equals to 1. Again, Cn equals to Cb. Cb is x, minus Nt is y, and Tb is 1. So in total, Cn equals to x minus y minus 1. X minus y is 2.5, so substitute x minus y by 2.5. So in total, we found out that Cn equals to 2.5 minus 1, that is 1.5. So Cn, this line segment Cn equals to 1.5 units in its length. In the next step, we repeated on rule 9 and implemented rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects the circles together passes for their touching point. Repeat again, if two circles touch each other internally, then the straight line that connects the circles together passes for their touching point. So in the drawing you have two circles. The center of this big circle is 0.0. The center of this small circle is 0.m. The straight line that connects the circles together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is actually point P. Again, according to rule 9, the straight line OM that connects the circles together must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to rule 9. So we can implement rule 9 in our drawing. Well, because in our drawing we have an internal notch between this small circle and this big semicircle at point K. That is to say they touch each other internally at point K. Therefore we can implement here rule 9. The center of this big semicircle is at point C. The center of this small circle is at point O. And the straight line that connects the centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through their touching point, that is point K. Again, the straight line CO must pass through point K, that is their touching point. Or COK is one straight line. Again, COK is one straight line according to rule 9. If COK is one straight line, it means that CO equals to CK minus OK. OK is one straight line, therefore CO must be equal to CK minus OK. So CO equals to CK. CK is the radius of the semicircle, that is x, minus OK. OK is the radius of this small circle, that is y. So in total CO equals to x minus y. But we already found out that x minus y equals to 2.5. So CO equals to x minus y, that is 2.5. CO equals to 2.5 units in its length. We already found out that Cn equals to 1.5 and On is the radius of the small circle, that is y. So in the next step I covered the right triangle OCN in a new page and implemented the Pythagoras theorem on this right triangle OCN. According to the Pythagoras theorem, in a right triangle, the square of their products equals to the sum of the squares of the perpendiculars. So this is right triangle OCN that I covered from the original drawing. In this right triangle OCN, according to the Pythagoras theorem, OC square, that is the square of their products, must be equal to ON square plus Cn square. OC is 2.5, therefore OC square is 2.5 square, that is 6.25, and it is equals to ON square. ON is y, therefore ON square is y square, plus Cn square. Cn is 1.5, therefore Cn square is 1.5 square, that is 2.25. So in total we found out that 6.25 equals to y squared plus 2.25. Here we subtracted 2.25 from this equation and found out that 6.25 plus 2.25 is 4, so 4 equals to y squared. Here we took out of this equation and found out that y, the radius of the small circle, equals to the square root of 4, that is 2. So the radius of this small circle equals to 2 units in its length. We already found out that x minus y equals to 2.5, but y is 2, so x minus y is x minus 2, that equals to 2.5. Here we added 2 to this equation and found out that x equals to 4.5 units in its length. 4.5 is 9 over 2. So the radius of the semicircle, the big semicircle, equals to either 9 over 2 units in its length, or in terms of numbers, it equals to 4.5 units in its length. Our test is to find out the area of this green shape. So according from the drawing, it is very easy to see that the area of the green shape because in total to the area of the big semicircle minus the area of the small circle. Okay, again, the area of the green shape equals to the area of the big semicircle minus the area of the small circle. The radius of the semicircle is x, therefore the area of the semicircle must be equal to pi x squared over 2. Minus the area of the circle, the radius of the circle is y, therefore the area of the small circle must be equal to pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total, pi x squared over 2 is pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4. So in total, this expression equals to 4 pi. We open the brackets of this expression and we found out that it is equals to pi over 2 and 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total this expression equals to 81 pi over 2 times 4, minus 4 pi. So it is 81 pi over 2 times 4, that is 8, minus 4 pi. Here we multiplied minus 4 pi by 8 and then we divided by 8 in order to account for of this expression. Minus 4 pi times 8 is minus 32 pi over 8. 81 pi minus 32 pi is 49 pi over 8. So if you found out that the area of this green shape, that is the area that we're looking for in this question, it is equal to either 49 pi over 8 square units in its size, so in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step, I presented to you the second question and we answered to the second question of this lecture. Our task in the second question is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the drawing you have a semicircle. It is given us the question that this is point O, that is the center of this semicircle. This is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. This is angle PQ. That is a right angle. This is angle PTS, that is also a right angle. Again, our test is to find out the length of this line segment PQ, that is equals to x. We have to find out the value of x. It is also given us a question that PT equals to TS. So if we define the length of PTSA, then TS must be also equal to A because they are equal to each other. So in the next step, we completed this semicircle to a circle. And we extended line segment TS until it touches the circle at this point. We define the touching point of the extended line segment TS with this circle. This point is point M. And we also join points P and M together by straight line. By doing all those constructions, we get the peripheral PTM is equal to 90 degrees in size according to what is given in the question. And peripheral PTM subtend on chord PM. Again, peripheral PTM subtend on chord PM. According to rule 5, any peripheral is equal to 90 degrees in size. This peripheral must subtend on the diameter of the circle. Therefore, peripheral PTM, it is a right angle, it must subtend on the diameter of the circle. Peripheral PTM subtend on PM, and therefore, according to rule 5, PM must be the diameter of the circle. Again, PM is the diameter of the circle according to rule 5. Point O is the center of the circle. Point B is the point of the circle itself, therefore OB is the radius of this circle. O being total equals to OS plus SB. So O being total equals to OS, that is 2, plus SB, that is 1. So in total OB equals to 2 plus 1, that is 3. So the radius OB of the circle equals to 3 units in its length. So the radius OP must be also equal to 3 units, and the radius OM must be also equal to 3 units in its length. In the next step we did a construction, that is to say, from this point S we do perpendicular on the diameter PM. Again, from point S we do perpendicular on the diameter PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point S and then the diameter PM. This point is point N. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle OSN, this angle equals to alpha, this angle equals to 90 degrees according to our construction, and therefore this missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in this upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, then the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the upper right triangle PQO is similar to the lower right triangle OSN according to angle similar to. So if you prove the proof will be like that. Those two angles are both equal to alpha, therefore they are equal to each other. Those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I shall prove that all the figures of this upper right triangle PQO are correspondingly equal to all the figures of this right lower triangle OSN. And therefore, those two right triangles are similar to each other according to angle similar to all. So if we found out that the upper right triangle PQO is similar, this is the sum of similar, to the right lower triangle OSN according to angle similar to all. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle OSN over side PT over side PQ of the right upper triangle PQO is equal to side OS of the right lower triangle OSN over side PO of the upper right triangle PQO. Again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side SN of the right lower triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the right lower triangle OSN over side PO of the right upper triangle PQO. SN is the missing side, so we leave it as it is. PQ is the line segment that we are looking for this question, and it is equals to x. We have to find out the value of x. SO is 2 and PO is 3. So in total we should find out that SN over x equals to 2/3. 2/3. Here we multiply this equation by x and finally found out that SN equals to 2/3 x. This is the missing side SN, that equals to 2/3 x. In the next step, we define this angle as beta. So in the green right triangle SNM, this angle equals to beta, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PTM, this angle equals to beta, and therefore angle beta is the common angle that belongs to both triangles. So this angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle this third missing angle must be equal to 90 degrees minus beta, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this small green right triangle NSM. So why those two right triangles are similar to each other? First of all, this is angle beta, that is a common angle that belongs to both triangles. So we can write down that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. So we should prove that all the three angles of this big right triangle PTM are corresponding equal to all those three angles of this small green right triangle NSM. And therefore those two right triangles are similar to each other according to angle similarity rule. So if it again, we should find out that the big right triangle PTM is similar, this is the sign of similar, to the right small green triangle MSN according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green triangle, SNM, over side PT of the big right triangle PTM is equal to side SM of the green small triangle NSM over side PM of the big right triangle PTM. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green triangle NSM over side PT of the big right triangle PTM equals to side SM of the green right triangle NSM over side PM of the big right triangle PTM. We have already found out that SN equals to 2/3 x over PT. PT equals to A, and it is equals to MS, SM is the missing side, so we limit as it is, over PM. PM is the diameter of this circle, the radius is 3, therefore the diameter is 6. So PM equals to 6 units in itself. So in total we should find out that 2/3 x over A equals to SM over 6. Here we cross multiply this equation and we found out that 2/3 x times 6 equals to ASM. 6 over 3 is 2 and 2 times 2x is 4x. So in total this equation 1 we have 4x. So 4x equals to ASM. Repeat again, according to equation 1, we have found out that 4x equals to ASM. In the next step, I presented to you rule 15 and we implemented rule 15 in our drawing. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Why? Because in our drawing we have chord TM that intersects with chord TB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. Repeat again. Now original drawing, chord TM intersects with chord AB at point S. So according to rule 15, the following equation will be true, that TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. Repeat again, according to rule 15, TS times SM equals to AS times SB. TS is A times SM. SM is the missing side, so we leave it as it is. So in this side of the equation we have A times SM and it is equals to AS. AS in total equals to AO plus OS. AO is the radius of this circle, that is 3, plus OS, that is 2. So in total AS equals to 3 plus 2, that is 5. Again, AS equals to 5 times SB. SB is 1. So in total we found out that A times SM equals to 5 times 1. 5 times 1 is 5, so according to equation 2, A times SM equals to 5. This is according to equation 2, while according to equation 1, we have already found out that ASM equals to 4x. So we have two different equations for the expression A times SM. Therefore, we get the equation 3 that states that ASM according to equation 1 must be equal to ASM according to equation 2. And again, we get that equation 3 that states that ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 is 4x, and it is equals to ASM according to equation 2. ASM according to equation 2 equals to 5. So in total, according to equation 3, we actually found out that 4x equals to 5. Here we divided this equation 3 by 4, and found out that x equals to either 5 quarters, or in terms of numbers, 5 quarters is 1.25 units. So we found out that the length of this line segment PQ is equals to x. It is equals to either 5 quarters units in its length, or in terms of numbers, PQ that is equals to x is equal to 1.25 units in its length. Okay, thank you very much.